Today we're going to look at something called momentum. So what is momentum? Well, momentum, you need to hear about, talked about in sports, is where one team seems to have everything going in their direction. The score or all the plays are going their way. And they talk about having to change momentum and how hard it is. Momentum in physics is, believe it or not, an equation. And momentum is essentially mass times velocity. Now, we call that P equals m times v. Why P? Because we already have m for mass. So momentum is known as P. I've had professors call it momentum to kind of help you remember what the P means. So if that helps, use it. Now, units for momentum are mass units times velocity units. So standard would be kilograms times meters per second. And that's what we expect to see. But it can be anything as long as it's a mass unit, grams or kilograms normally, and a velocity unit, which could be meters per second. That could be kilometers per hour, centimeters per second if we're talking about something on a shorter scale. But that's what we see. But the big thing about momentum, and this comes up again and again, is that it is a vector quantity, which means it has a direction. So we're going to see positives and negatives with momentum. So an object momentum is hard to stop. If something has a good mass and velocity going that way, it's going to take something hard or something very, very firm, a very good force to stop it, to change its momentum. So football is going to be applied here quite a bit in some of these situations. But in football, a defensive player applies a force to stop the momentum of an offensive player with the ball. So defensive players apply a momentum to stop an offensive player. Now, a lot of words here. I'm going to read it and then we're going to discuss. A force acting for a given amount of time will change an object's momentum. In another way, an unbalanced force always accelerates an object. What's this? Now we're talking about Newton's first law. If the force acts opposite the object's motion, it slows the object down. If it acts in the same direction of the object's motion, then the force speeds the object up. Either way, a force will change the velocity of an object. And if the velocity of the object is changed, then the momentum will change. So to change momentum, we have to change velocity. To change velocity, we have to accelerate it. And to accelerate it, all of a sudden, the second law and the first law come into play. So Newton's laws are going to be seen a lot when we talk about momentum. Now, Newton's second law, F equals ma. Or A, if you recall, is change in velocity over change in time. So we can write it also this way. Now, if we take this equation, right, force equals mass, so I'm going to try to put it in levels here, delta V over T. If we multiply both sides by T, T's cancel, and we get this. F times T equals m times delta V. This is F times T, we call impulse. Mass times change in velocity. Mass times velocity is momentum. Mass times change in velocity is change in momentum. Which leads us to say impulse is equal to change in momentum. So there's our equation. Let's talk about what this means, right? We'll go back here for a second. Impulse is force times time. So it's how long the force is applied. Will equal the change in momentum, or mass times the change in velocity. So if the force is applied with the motion of the object, it will have a positive change in momentum. But if it goes opposite, we would probably see a negative change in momentum. And that's what we have to think about, okay? Directions, force applied, and so forth. So now let's look at a rebound collision. So we got a tennis ball going against the wall. It's traveling 10 meters per second, hits the wall. It bounces back in the opposite direction at 5 meters per second. Positive 10, negative 5. Change in velocity. Final velocity, negative 5, minus initial velocity 10. The change in velocity is negative 15. Let's look at case B. we got positive 30, and we got negative 28. Change in velocity, negative 28 minus 30 equals negative 58. The greatest change in velocity, case B. The greatest acceleration, change in velocity over time, we'll assume the time's the same, 1 second. The change in acceleration, case B. The greatest momentum change, the change in momentum, okay? Change in velocity multiplied by mass. Masses are the same because we're having the same tennis ball. Greater change in momentum for case B. And greatest impulse, because impulse is equal to momentum change, case B also has the greatest impulse, so all B. Looking at a graph, we're looking at velocity change, right? In case A, we're going from 5 to negative 3, so negative 3 minus 5. Negative 3 minus 5 is negative 8. Here we're going to negative 1, right? Negative 1 minus 1, 2, 3 is negative 4. So the greatest velocity change, case A. Greatest acceleration over change in time. So let's go, we got from 3 to 4.5. We got from 3 to 4.5. So we're dividing that by 1.5. Don't have to do the math to figure out that case A has the greatest acceleration. Greatest momentum change, the greatest change in velocity is going to be A, and the greatest impulse is the same as momentum change. That's also A, case A. Here we got a half a kilogram carts pulled with a 1 Newton force for 1 second. So we got this cart pulled that way. 1 Newton force for 1 second. Another cart is pulled with a 2 Newton force for half a second. Which cart has the greatest acceleration? They both have the same mass, right? So force times time. 1 times 1 is my impulse is 1. 2 times 1/2 is an impulse of 1. So they both have the same impulse. So which one has the greatest impulse? Neither. They're the same. Which one has the greatest change in momentum? Okay? Well, the greatest acceleration is going to be greatest change in velocity, right? So let's look. This one is, if our impulse is 1 and our mass is 0.5, what's our change in velocity going to be? Well, I divide by 0.5, so 1 divided by 1/2 is 2. My change in velocity is 2. So my change in velocity is 2, so that means my acceleration is going to be 2 divided by 1. Here I have 1.0, and that's my impulse. And I'm going to multiply that by my mass of 0.5. So my change in velocity is also 2 for the second block. But the second block takes place over half a second. So its change in velocity is 4. I'm sorry, its acceleration is 4. So the greatest acceleration is cart 2. Same impulse, because they both have a 1 for the impulse. So what is the greatest change in momentum? They both have the same change in momentum, because impulse and change in momentum are the same thing. So in a collision, an object experiences a force for a given amount of time. That's our impulse. And it causes a change in velocity. And that's our momentum change. And again, Ft equals m times delta v. Effective collision time upon the force. So if we're applying a force of 100 for 1 second, our impulse is 100. If we apply a force of 50 for 2 seconds, our impulse is 100. So if we want to apply the same impulse as our force goes down, right? As our force gets smaller, our time has to increase. So as force goes down, time has to increase during the force. So you have to apply the force for a longer period of time to get the same impulse. Big T, little f, right? And so we're going to look at time and force here. If our time is greater, so if we hit the punch and hold the punch, right, for a long amount of time, rather a soft punch or a hard punch, the change in momentum will be given. But if we take a greater force over a smaller amount of time, we could still have the same change in momentum. So if we throw a harder punch, but stay connected for a short amount of time, could be the same change in momentum as applying a small force over a longer period of time. So, things to think about, right? If we ride the punch, it increases the time of collision and reduces the force of collision. Okay? So the longer we keep the punch in, the less force we need to have that change in momentum. So think about a car wreck, like a car bouncing or rebounding. So in case A, the car's traveling 5, hits the wall, bounces off, and is going back 4. Okay? Our change in velocity, -4 to -5, is -9. In case B, we hit the wall and crumple, right? The car has a change in momentum of or change in velocity of -5. All right? So our velocity change is greater. Okay? Our velocity change is greater, which causes a greater change in momentum. Which means that if we want to do some math, so let's keep the mass the same. So let's go force. Force pen is not working. Force times time is equal to mass times delta V. So for case A, my change in velocity is -9. My mass is the same, so I'm going to say the mass is 1, is equal to force times time. Now, my time is minimal, right? So my time is really small. So if my time's really small, my force is really high. So a really high force we have going on here. But in case B, force times time is equal to -5. But if my time of collision is increased, my force goes down. And that kind of explains why cars crumple instead of bounce. If you're in a car and you were to hit a wall, if the car didn't crumple but bounced, though your car probably wouldn't be damaged, your body could be because of the force of the collision. So something to think about is having a car that crumples is a lot better than having a car that bounces. Hence, that's why cars have crumple zones.